point that I should mention this afternoon, I'm facing some issues with network connectivity in the department. So in case I drop out of the meeting, just wait, be patient. I'll rejoin as soon as that network connection comes back. Okay. So in case you find me out of the meeting, you just wait. So let us start now. What I have studied so far or discussed so far in this course, that in the first lecture we discussed about the types of system. Okay, I think I had only one lecture, right? It is on the second lecture.
Yes, sir.
Yes, sir.
So we discussed about the definition of system, and we try to identify different types of system, and then we studied the system properties. And finally, we discussed some methods to ascertain the system properties. That is, whether they are linear, non-linear, time varying, time invariant, things like this. In this regard, we concluded our lecture on the last class, if I remember, on the classification between dynamic system and non-dynamic system. And we have seen that the dynamic systems are those which, upon excitation, shows a transient response before settling down to a particular or new set value. Whereas non-dynamic system exhibits no such transient, and it directly moves from one steady state to another steady state. Fortunately or unfortunately, most of the physical systems that we encounter are mostly dynamic in nature. That is, whenever you put an excitation or give an input, the output will change its state, but the change will take place via a transient, where the output will be showing some different types of nature in terms of responses. So, in our course, we shall be deriving a mathematical expression for description of such dynamic systems. And as I've already discussed in the last class, that the physical properties of these dynamic systems are described by integral differential equations. So given a dynamic systems, we have to first obtain the integral differential equation that describes its dynamic behavior. So from the differential equation, we can obtain the nature of the system. So first of all, the differential equations will characterize the physical system, and from the nature of the differential equation, we can determine the type of the system. How? Say, for a given system, there may be different types of differential equations. First of all, say second order system. So in this case, this is u. So this is a second order differential equation with the coefficients a, b, and c being constant. This is case one. Another case may appear where we may have a differential equation. Obviously, it should be noted that these are all functions of time, this xt. In this case also, these are all functions of time. Otherwise, you would get confused. So in the second case, see the differential equation coefficients are not constants. They are function of time. The time is normally regarded as an independent variable. Okay, so the differential equation coefficients are functions of an independent variable time. So the third case may appear where this a will be a function of say x and u. B may be a function of another function, say this is f1, this is f2 of x and u, plus c another function of x and u. Sorry. In this case, the coefficients are function of some dependent variable. That is the system variables x, and u is the input variable. So there may be distinct three cases that we can arrive at. So this, from this differential equation itself, you can comment on the nature of the system. That is, if the constant coefficients, if the coefficients of the differential equation describing a dynamic system are all constant, or
Sir,
if the coefficient,
sir, someone is trying to join, I think.
Okay. Actually, when I'm in meeting, when I'm presenting, I don't get that notification. Right. Okay. You just intimate me. Yeah. Whenever your friend is trying to join, you just intimate me. So there were two situations where the coefficients of the differential equation describing a dynamic system are constant, or they're a function of time, which is an independent variable. In such cases, these systems will be linear system. But if the coefficients of the differential equation are functions of not only time, they are functions of, suppose, some other dependent variables. In this case, the dependent variable is the system variable output x. In this case, the system will be termed as nonlinear system, because in this case, the system will not follow the principle of superposition. So in this case, this will be nonlinear system, where the coefficients will be function of a system variable or some dependent variable. But if the coefficients are functions of time only, then what you will get will be a linear system. But in this case, this linear system will obviously be time varying one, where the coefficients are all functions of time. So this is a time varying linear system, and this differential equation where all the coefficients are constant, this will be linear time invariant system with constant coefficients in the differential equation. Fortunately, in our case, we will be mostly concerned about the dynamic equation of this linear time invariant system, right? Now, why this differential equation is required? To obtain a mathematical model of the physical system. Now, what is the purpose of the differential equation? Now, by simply solving this differential equation, we can arrive at the solution, that is xt, or the desired response to the output that we can analyze. For that, we will be using different tools for analyzing. The tools are mostly mathematical in nature. So that requirement is that you should develop a mathematical model so that the mathematical tools can be used to obtain the solution of this differential equation and to analyze the system or to synthesize the system. Okay. Now, the two basic avenues that will generate from this differential equation in respect of analysis are classified as the concept of, just a second, I'm getting a call. So this is a concept of the first avenue that will generate from this differential equation is the concept of transfer function. Do you have an idea about transfer function? What is the transfer function?
Yes, sir.
Okay, how do you define a transfer function?
Sir, transfer function is the frequency domain ratio of the output response and the input response with all the initial conditions set to 0.
Okay, that is fine. So, okay, you have a basic idea of transfer function. So, in the consequent time, we will be developing in-depth analysis of on transfer function. That is the application of transfer function, why the transfer function is necessary, and what are the limitations of transfer function. and how the transfer function limitations can be overcome. So the first and foremost limitation of transfer function is that it is only applicable when the initial conditions are 0, and it is only applicable for linear systems, right? For nonlinear system, or linear time invariant system rather. For nonlinear systems or time invariant system, the concept of transfer function doesn't hold. So this is only restricted to LTI system with 0 initial condition. So such restrictions will obviously restrict the functionality or the applicability of transfer function. To eradicate this, we have another avenue, where the differential equations will be cast in state space. That is, we'll develop a state space model or state variable model. Okay, in this case, the concept of initial condition is valid. For finite initial condition, you can obtain a mathematical model. Further, this is applicable to linear, nonlinear, time invariant, time varying, all sort of systems. So state space model will be much more versatile in terms of its applicability. So in due time, we'll discuss about this transfer function and the state space model. So first of all, we came to know that to analyze a dynamic system, we have to first obtain this mathematical model. So the mathematical model will obviously be described in terms of differential equation. Now let us first consider, given a physical system, how this differential equation model can be obtained. Now for physical system, the differential equation model can be obtained by using the physical laws of the process. Now what are these physical laws? There is common physics, laws of common physics. But that will constitute two very fundamental steps. What are these steps? The first step is that one should build up a physical model of the system that is based on an interconnection of idealized system elements. So first, you have to build up a physical model of the system. A physical model will be interconnection of idealized system একটু হোল্ড করো so it will be an interconnection of idealized system elements. Now the question, so the physical model will be first developed based on the interconnection of idealized system elements. Then this physical model will be described in terms of elemental laws of physics. Laws of physics or engineering, whatever you say. So what are these idealized system elements or why they are necessary? Because we all know all physical quantities are very complex in nature, because we very seldom we find a system or a physical component which is completely linear in nature. So most of the physical components that we obtain are nonlinear in nature, and above all, the system components, they are so interconnected, so overlapping, or they are so interacting that it's very difficult to obtain a physical model of a particular system which is simple enough for analysis. So what we have to do, we have to start from a very basic point. And what is this basic point? We have to obtain a very simplified system model. And that will be constituting of this idealized system elements. Idealized means some of the nonlinear features will have to be eliminated or has to be discarded, should not be considered at first stage. Some of the interaction between different systems has to be discarded or should not be considered at the first level. In this way, we obtain some idealized physical element. So there are two very important points that should be noted in terms of this idealized physical elements or system elements. First of all, the spatial distribution is neglected. That is, it is considered to be a point phenomena. What does this mean, spatial distribution? Suppose You want to model a mass. So a mass will have some distribution. It will not. It will have some dimension, physical dimension. But for the purpose of mathematical modeling, what we will do, we'll consider the mass to be concentrated at a point, say CG, of the physical system, and by this way we can consider this mass to be acting at that particular from that particular point only. Similarly, if you want to model the temperature in a particular room, at various points in the room, the temperature will be different. But if you want to represent the room temperature with a single value, you can find a mean position in the room and represent the temperature by the temp of the room by the temperature at that point only. So by this way, you can obtain a model that is called, sorry, a lumped parameter model. Another common example of a lumped parameter model would be the resistances. We consider the resistances or the capacitance to be concentrated at a particular point while developing the electrical equivalent. But actually they are distributed. So the spatial distribution is neglected and they are considered to be point phenomena. And this is called lumping. And such models are called lumped parameter models. So our first objective will be to neglect the spatial distribution and consider the system element to be described by a lumped parameter model. The second point, I think I'll show you, I have a written note over here. I'll show you from this itself. So first of all, you have to disregard the spatial distribution, and then it is assumed that the variables associated with the element lie in a range so that the element can be described by simple linear law. What are the laws? A constant of proportionality, a first order derivative, a first order integration. Obviously, B and C, they can be interchanged because integration and derivative can be obviously interchanged. So the first thing is that you consider the element to be lumped. The second thing is that the variables associated with the element are in this range so that they can be described by these simple laws. These are all linear laws. There's constant of proportionality, a first order derivative, and first order integration, and nothing else. So this is a couple of simplifying assumptions that should be followed to obtain the idealized system element. Now, once you obtain the idealized system element, let us now discuss about the variables associated with an idealized system element. To simplify the matter, let us consider a single port network. There is a system having two ports. This is an example. One is the input port and there is the output port. Now, in this case, it's taken being. Actually, this is the input port and this is the output port. Now, the variables associated with such ideal element, this is an ideal element. And the elemental law that it follows is something like V0 equal to f of Vi. So this may be V0 or this may be I, whatever. Now the variables associated with this ideal element can be classified broadly into two categories. What are these categories? First one will be true variable. What is true variable? True variable means it sort of passes through the element and has the same value at the input side and at the output side. That is, whatever value is going over here, the same value is coming over here. Just like in current, so in resistive element. Okay, so this is a true variable which just passes through the element or the ideal element. Another one will be your across variable. What is the across variable then? Across variable is that which appears across the element. How? So the voltage will appear across these two terminals. So this will be across variable. So in terms of ideal element, there will be two types of variables associated. In terms of its nature, if it appears across the element, it is called across variable. If it possesses the same value in at the input port and out of the output port, then we call it a true variable, that it doesn't change its value when passing through the element. Common example will be current as a true variable and voltage as an across variable. Now, this is not a fundamental classification of the input signal, of the signal variables associated with an element. What is the fundamental classification? These are the input variables and output variables. Input variables means the variables that are affecting the ideal element, and output variable is the effect or the response in response to the input variable. So the cause and effect. So in this case, an input variable may be true variable or across variable. Similarly, the output variable may be true variable or across variable. If we apply a voltage source and measure the current, then your input variable is voltage or across, and the output variable is current, that is true variable. Now, if you apply a current source and apply the voltage across a resistance, then your input variable is current, which is a true variable, and output variable is voltage, which is an across variable. So these are interchangeable. The combinations are interchangeable, but these are the basic definition: input and output variable, and the nature may be across variable or maybe true variable. So once we have decided the types of variables associated, let us now consider a
Sir,
physical. Bolo?
sir, can you please explain the across variable and through variables once more?
Okay. Across variable means whichever variable, whichever value it takes while entering the element at this input port is the same value it appears out of this output port. Just like a current. If we have a resistance as an element, and if current flowing in is I, and current flowing out will be I, so this is an across variable, a true variable, sorry, this is a true variable. But the potential across this will have a value IR, and it appears across these two terminals. Across these two terminals, the voltage drop. That's why this voltage will be called an across variable, which appears across the two terminals, and current is called a through variable because it is passing through the element without any change. Whatever value it takes while getting into the variable, into the element, it takes the same value while getting out of the element. That's why it's called a through variable. Wherever a variable which appears across the terminals of an element is called an across variable. Yes, sir.
Yes, sir.
So let us consider a mechanical system. Basically, mechanical systems can be modeled by means of three ideal translatory and three ideal rotary elements. And obviously, you can consider the additional incorporation of gear, okay, or gear trains. Now, the mechanical, I think mechanical modeling, I'm considering this mechanical modeling because this will help me in developing the mathematical model. The first element is nothing but a mass element, M. If a force F is applied, then this force will be described as m d2x dt square, where x is the direction, and in terms of velocity, it will be m dv dt. Second element is a spring element. These are the fundamental mechanical elements that will constitute a mechanical structure. Second element, these are all translational, first of all. So second element is a spring element. The spring element is an energy storing element. What happens if you put a force F over here? This portion, say A, will deflect by an amount say x1, and B terminal will deflect by amount say x2. So what will be the net deflection? x1 minus x2, and the force will be given by k into x1 minus x2 or k into x being the equivalent displacement of the spring x1 minus x2. Right? This is the contraction of the spring, the amount of contraction of the spring. So this is the fundamental equation deriving or describing the force acting on a mass, and this is the force acting on a spring. The third element is the damper element. So what is that? Do you have any idea? It is a damper. Spring, I guess you all of you know spring, mass. Damper is nothing but it's an element where no energy is stored, rather it dissipates energy. And a basic common example of a damper will be a shock absorber in a bike. Have you seen a shock absorber in a bike where there is a piston within which another piston is inserted, and whenever the road becomes unable, that particular outside the piston in the outer periphery will contract and the inner piston will get sucked into the outer one, so that the road roughness is dampened out by this damper. What actually happens is that within this piston, within the cylinder, there is some viscous fluid present. And whenever a force is applied over here, this piston tends to move in the direction of the force. And this faces an opposing force from this viscous fluid. And that generates an repulsive force. And that tends to dampen the effect of the force. And this can be expressed in this way. If the deflection of this side is x1 and deflection of this side is x2, corresponding velocity being v1 and v2, then the force can be expressed as f of v1 minus v2 or f into v. That is with respect to the relative velocity. Right? In some of the cases, we find damper force represented in terms of x1 and x2. But in all our studies, since we are considering viscous fluid, we shall consider this notification. That is, force, repulsive force produced by a damper is proportional to relative velocity of the two terminals, right, of a damper. So these are the three basic fundamental building block of translational mechanical system. Equivalently, for rotational mechanical system, there will be three fundamental blocks. What are these? First of all is the inertial element. It is nothing but a mass, but instead of translational motion, it is free to rotate about an axis. So if you produce a torque, provide a torque T, there will be an angular displacement theta and angular velocity omega. So it will rotate in this direction. So for the torque T will then be expressed as J d omega dt or J d2 theta dt square. Right? This is angular displacement, angular velocity. And this is the torque applied. And J is the inertia. This is similar to the mass of a translational motion system. Similar to the translational spring, there will be a torsional spring, where if you produce a torque in this side, say side A, this side will move by an angle theta1 at an velocity omega1, angular velocity, but the other side will be deflected by an amount theta2 with an angular velocity omega2. So the torque will be expressed as T equal to K, theta1 minus theta2, or K into theta, the net deflection or the relative deflection of the two terminals of a spring. So it will be proportional to this, and K is the spring constant that describes the nature of the spring or stiffness or hardness of the spring. And third element will be a rotation damper, same as one, only that it is now free to rotate in this medium. So whenever you apply torque, it will be opposing the movement. So one side this damper will move to theta1, the other side will move by effective omega1 and omega2. Then the torque will be the extension, will consider this extension to omega1 and omega2. In this way, you can describe any mechanical system, there is a translational one or rotational one, by this simple laws. These are element laws of physics. These elements, this mass, spring, damper, they are all idealized elements. You assume this type. So next, if you consider just of this element, we have inertia and the two kinds of springs, they are the energy storing elements, where the energy is stored and retrieved. Now, for mass, you know, the energy stored is half mv square for translation motion, kinetic energy. For rotational motion, it will be half omega square. Similarly, for spring, for a translational spring, the energy produced is
Sir,
half
your
kx
voice is
square.
not coming properly.
Is it so?
Yes,
এবার
sir.
আসছে?
হ্যাঁ স্যার এবার আসছে।
Okay, okay. Some problem with the mic. So, the translational speed, the potential energy or the deformation energy will be given by half kx square. For torsional speed, it will be half k theta square. Okay? So, the mass and spring are the elements which can store energy, and energy can be restored from mass and spring. Whereas the damper is a dissipative element. This the power consumed lost in the form of heat because the piston is moving in viscous fluid, there will be a lot of friction and heat will be as a dissipation of the energy. So this is a dissipative element. Now if you find or think about the analogy, see that mass and spring are something like capacitor and inductor. I'm not directly connecting capacitor to mass and inductor to spring, but it's something like capacitor and inductor because both of them can store energy, right? Whereas the damper is something like resistance, cannot store energy. What it can do is simply dissipate energy in terms of heat. Let us now consider how this mechanical systems or this electrical systems can be related. For that, let us first consider the example of a translational system where a mass m is attached to a spring of stiffness k and a dashpot or damper of viscous friction coefficient f. And upon that mass, force F is acting in this direction, upward direction, so that mass moves from its neutral position by an amount x. So this is a displacement. So you have to obtain mathematical model for this mechanical system. Now how that can be obtained? First of all, you have to obtain the free body diagram. I guess all of you know the free body diagram, the concept of free body diagram?
Yes, sir.
Okay. So the free body diagram for this system will be something like this: mass, force F acting in this direction. The spring will be producing a repulsive force in this direction, downwards direction, to oppose the motion. Similarly, damper will be producing a repulsive force in this direction to oppose the motion. So is this all or something else is missing from this free body diagram?
Sir, wait.
Right, the mg component.
Yes, sir.
Right, the mg component is not given. For that, there is a trick. If you follow that, the mg component will not be necessary. What is that trick? The zero position or the null position is considered at a point where the spring and mass are in static equilibrium. At that point, you consider that position to be zero position. What does that mean? Suppose this is a free spring, this is the end of the free spring. As soon as you suspend the mass m, say from this point, what will happen? Due to the weight of the mass, this spring will get elongated by this amount. So delta x, right? So if it is getting elongated by an amount delta x, the amount of elongation will be enough to counteract this mg component or the weight component. Agreed? So at steady state, if the spring is elongated from this point to this point, say by delta x amount, this delta x amount or the energy stored in the spring or the work done by the spring is exactly equal to the weight component of the mass. Now, if we consider this new position to be your reference position instead of this one, the previous one, then the mass component, mg component, is already being taken care of by the delta x expansion of the spring. Agreed?
Yes, sir.
So you did not worry about this mass component. But if you consider, so actually what will happen, the effective length of the spring, if it was initially x, will now be delta x. That will be your starting length of the spring. So whatever deflection you are considering for the spring will be over and above this x plus delta x. because x plus delta x is now your initial condition or initial length of the spring. And delta x, what is the function of delta x? It is actually counterbalancing the mg component of the mass, right? That's why your equation will be much, much simpler, right? So this is a trick that we are following here to get a simple mathematical expression. And this is a valid assumption. There is no if and but over here. Simple as that. So from the free body diagram, what you can write? The force balance equation will be something like this. So ultimately, you'll get an equation like this. Now I'll just write down these expressions over here for mass spring damper. What is the expression you're getting? Force is equal to mx double dot plus fx dot plus kx. Okay, right? So I'm just taking a note of this case. Now let us consider what happens with a differential equation. It's a second order differential equation. See, second order differential equation with constant coefficients. So since it's a constant coefficient differential equation, it will be linear time invariant system. First of all, second of all, why the differential equation is of order 2? Because it has two energy storing elements. What are these two energy storing elements? The mass and the spring. So you should keep this in mind. The order of a system or order of the differential equation, which is same as the order of the system, is determined by the number of energy storing elements present in the system. Had there been 3 energy storing elements, the order would have been 3. Things like this. Understood? Okay. And you have to first identify the number of energy storing elements present in the system. And then you will see always in the case that the total number of energy storing elements will determine the number of or the order of the system. Now let us consider a rotation motion, a rotational system. Now the concept of rotational system will be very, very important when you will be studying rotating machinery, right? Like electric machines, DC machine, synchronous machine, induction machine. So the modeling of this rotating machinery will involve these rotational systems, although the concept is very much similar to that of a translational motion. Only thing is that you have to replace the translational force, displacement, and velocity by torque, angular displacement, and angular velocity, right? So the 3 basic components in this case, what are these 3 basic components? Moment of inertia, a torsional spring, and a viscous friction. And what are the variables of interest? The torque, the angular velocity, and angular displacement. These are the variables of interest. Now let us consider an example. What is the example? A rotational mechanical system is there. It consists of a rotatable disk which has a moment of inertia J, and it is connected via a shaft which has a stiffness K. So this is a torsional spring basically. Now the disk is rotating in a viscous medium. This is a viscous medium, and the viscous friction coefficient for this medium is F. Now if we apply a torque T that produces an angular displacement of theta or angular velocity omega, now you have to obtain the mathematical expression for this system or the differential equation for this system. So what is the first step? You have to draw the free body diagram in this case. So this is the free body diagram where this is the force applied. So the component, there is a viscous friction coefficient component will tend to oppose that. K theta will tend to oppose that as well, right? Similarly, the component of inertia will also tend to oppose the motion. So the entire equation will finally take this form. This is, if you go back to the original equation, so it will be same as that equation. The only difference is that in this case, the elements are angular velocity, dt, angular acceleration, and angular displacement, right? So you can write T equal to J theta double dot plus f theta dot plus k theta. So these are the two equations. This is a translational motion and this is a rotational motion. Now let us get back to what we have been. Now the thing that I was talking about, the elements like mass and spring, they're like capacitor and inductor. They can store energy and that energy can be restored. Whereas a damper is like a resistor where the energy is only dissipated. You cannot store any energy. So let us consider now an electrical system. Okay, what is the electrical system? It's a series RLC circuit. So this is a given series RLC circuit. If we apply KVL, what will be the KVL equation? L di dt plus Ri plus this is a potential drop across the inductor, potential drop across the resistance, and potential drop across the capacitor. 1 by c integration I dt. This is again the output. The capacitor voltage is supposed to be the output of the circuit. Now, if we consider the fact that I, the current is nothing but, sorry. That current is basically nothing but rate of charge accumulation. So, from the given equation, L di dt plus Ri plus 1 by c integration I dt, or charge is nothing but integration of I dt. So, following these two relation in this equation, what you will ultimately get? L dq d2q dt square, that is from L di dt. Ri will be R dq dt, and this will be 1 by c into q is equal to E. What is E? E is the forcing function here. That is the voltage that you apply to the circuit, which will drive this current I in the circuit. So this is the equation describing the dynamics of this RLC series circuit. Let us write down this equation now again. Your forcing function is E, a voltage source. So the equation become L q double dot plus R q dot plus 1 by C q. Okay. Next, let us consider a parallel RLC circuit. এটা বুঝতে পারলে তো কি হচ্ছে জিনিসটা? জাস্ট এই ইকুয়েশনটাতে we are replacing this I by dq dt. Because current is nothing but rate of charge accumulation. So from that we obtain this second order differential equation. Why you are getting a second order differential equation? Because there are two energy storing elements, the inductor and the capacitor. But the resistance is a dissipative element, it cannot store any energy. Next, let's consider an RLC parallel circuit which is being excited by a current source of I. So applying KCL, what we'll get? C d dt, the potential drop across each of the elements is E, plus this is the current through capacitor, 1 by L integration E dt, that's the current to the inductor, and E by R, the current to the resistance. So all this should sum up to I. Now in terms of flux linkage, you can write phi equal to integration of E dt, or E is equal to d phi dt. If we put this relation and this relation into this equation, so finally what you will get? C d2 phi dt square plus 1 by R d phi dt plus 1 by L phi is I. I is the forcing function of the current that we are talking about. Just we replace E by d phi dt and integration E dt by phi, right? So this will lead to this will lead to this will lead to this. So if we write down that particular expression now, you can write the forcing function representing capital I is equal to C phi double dot plus 1 by phi dot plus 1 by L phi. So these are the four equations. What are the four equations? This is the equation for a mechanical translational system, equation for mechanical rotational system, equation for series RLC circuit excited by a voltage source, equation for parallel RLC circuit excited by a current source. Now, why I am writing these equations? There should be something important with these equations. The important characteristic is that suppose you consider this equation or this equation, the nature of these equations are all same. They're identical in nature. That is, they are constant coefficient differential equations of order 2, where the coefficients are constant, right? So there will be certain similarities between these equations. And what does this equation imply? These equations imply the dynamic behavior of a system. So any system which is characterized by either of these differential equations will exhibit similar dynamic behavior. That's why this sort of systems are called analogous system. Right. The concept of analogous system is that a group of systems for which the dynamics can be described by an unique, there's only one differential equation. So then the group of system will be called an analogous system. See, so that means that mechanical translational system can be represented in terms of series RLC circuit or in terms of parallel RLC circuit. Similarly, the rotational translational system can be represented in terms of series RLC circuit or parallel RLC circuit. Now, what is the advantage of this concept of analogous system? Suppose you want to study a mechanical system which comprises of very large mechanical components. But if you want to analyze or synthesis the performance, it's very difficult to exert different experimental steps on that particular setup. And also the setup may not be very mobile. So you have to work at the area itself, the live area itself. So on the other hand, if you can have a mathematical model of the system, say it's derived by a second order differential equation, then you can simulate the similar response or the similar behavior by a combination of series RLC or parallel RLC circuit. The value of L, R, and C will be a function of M, F, and K of the system. And then whatever be the value that is coming up, you can suitably choose your L, R, and C values based on your calculations. And that electrical equivalent of mechanical system will be sufficient to study the dynamic behavior of the system. So what are the advantages? You don't have to exert or examine the actual mechanical system. You can simply obtain a mathematical model. You can fabricate the model in respect of RLC circuit because the electrical analogous systems, because electrical systems are amenable to experimental study. They're easily available. They are very easy to carry out different experiments. So by this way, we can obtain a mathematical model, and then followed from that mathematical model, we can obtain electrical analogous system corresponding to mechanical system. Not only mechanical, any system that has a particular differential equation can be converted to an equivalent electrical network. And since electrical network is very easy or amenable to experimental study or analysis, you know the different rules for analyzing electrical network. So it will become very easy to at least predict or study the behavior of the system, right? And one thing is to be mentioned here that whatever mathematical modeling we have done so far are based on very simplifying assumptions. That is, there are linear idealized elements are the basic components of the mechanical, electrical, or whatever system it is. But in actual reality, there is no such case. The life is not that simple. So there will be nonlinearities here and there. There will be interactions here and there. So you cannot write this simple differential equation with constant coefficient to describe actual behavior of the system. What you get is only an impression, a scaled down impression, or a representative impression of the behavior of the system. That will be your basic starting block regarding the response of the system or behavior of the system. You should not be judgmental. based on that particular behavior of the system, because the practical behavior may be completely different with respect to this idealized model. Right. So what will be the next step? In the next step, once you're satisfied with the study or synthesis, you just incorporate another level of nonlinearity, a level of nonlinearity. Then you study and see the results, whether they will be much more in agreement with the actual result. Then in the next stage, when you're satisfied with that stage, in the next stage, you apply or incorporate in your model another level of nonlinearity. And you see, if you keep on increasing this level of nonlinearity interactions or neglected interactions or dynamics, the system behavior will be much close to the behavior of the model that you have developed. Then the question may arise that how much nonlinearity or how much of this actual scenario can we incorporate in a mathematical model? So we can go on incorporating the actual behavior or incorporating the complicated nonlinear behaviors in your model until and unless you reach a point of diminishing return. Now, what do you mean by point of diminishing return? Beyond that point, a certain increase in the complexity of the model will produce only a minor increase in the performance of the model with respect to the actual performance of the system. That is, the similarity between the model response and the system response will improve by only meager amount, only very, very small amount. So entire burden that you're taking, the mathematical burden that you're taking in modeling the system with that level of complexity and studying the response of the system with that level of complexity is yielding only a slight percentage of improvement in the performance with respect to the actual performance. At that point, there's no point carrying out this process of incorporating complexity. So because you have reached a point of diminishing return. And in some situations, you might reach a point of no return. That is, whatever value or whatever complications you incorporate in the model, it becomes so complicated that you don't get any improvement in the model response as compared to the plant response, the actual plant response. Because at the end of the day, your objective is such that you develop a model, be it linear or nonlinear, the response of the model should be following the response of the actual system as closely as possible. Whenever you find that incorporation of such nonlinear phenomena into the modeling makes the model so complicated that the improvement in the response with respect to the previous level is very, very small, the entire burden of this mathematical modeling will be at no cost or will be of no help. So you should stop there. So in this way, definitely we follow a hierarchical pattern of modeling. For your case, we'll be only considering the model of a system in the form of idealized system elements with a differential equation comprising of constant coefficients, right? Now let us draw the analogy between the mechanical system and electrical system. So there may be two analogies that you can have. First analogy will be force voltage. And obviously this could be torque voltage. So for translational, it will be force voltage analogy, or for rotational, it will be torque voltage analogy. What does that mean? We represent this mechanical system by an equivalent series RLC circuit. Similarly, in other half, what you will have? You will have torque or force current analogy. That is, the mechanical system, whether translational or rotational, will be represented or replaced by an analogous electrical system comprising of parallel RLC elements supplied by a current source. Now, what you have to do, given a mechanical system, you know F, M, and K values, or J, F, and K values, you have to calculate corresponding L, R, and C values. Now, how that can be done? if you look at the equations, first of all, let us consider force, voltage, or torque voltage analogy, right? So what is the basic forcing function? It is like, sorry, I should use a proper color. So it will be torque or force, and that will be replaced by voltage. See, force, torque, it will be replaced by voltage in electrical analogy. Next, mass or inertia or mass, that will be replaced by
Inductor.
right, inductor. Just we are following the equation, coefficient of the equation. Then what about F? Both the cases it is F, no issues. So it will be replaced by the resistance.
Resistor.
Right? What about spring stiffness, K? Is K, torsional spring and normal spring. So K will be replaced by inverse of the capacitor, or C will be equal to 1 by K. So these are the elements. What are the variables? The angular displacement or displacement will be represented by charge. Sorry. Right? And angular velocity or linear velocity, that will be replaced by current. Right? So this will be your force voltage analogy. So in RLC circuit, your L value will be same as M value, R value will be same as F value, and capacitor value will be same as 1 by K. So this will be a series RLC circuit supplied by and voltage source E. Similarly, if you want to develop a force current analogy, then your torque or force will simply be current, right? Your inertia or mass, what will be this? Capacitor. Your friction coefficient will be 1 by R. Your spring constant will be 1 by L, or you can say R is 1 by F and L equal to 1 by K. Similarly, your angular displacement or translational displacement will be nothing but phi. What is phi? Phi is nothing but magnetic cross linkage. Okay, and your velocity, angular velocity or displacement velocity, translational velocity will be d phi dt, and that is nothing but voltage. So if you replace or represent the mechanical translation or rotational system by an equivalent parallel RLC circuit, then this will be the components that you need to have. So this analogy will help you analyze the mechanical or any other system in terms of electrical system and carry out experiments in a laboratory environment. Okay, because electrical systems are much more easier to work with rather than mechanical systems. Right? Now let us consider a physical example where we will be applying the law of the mathematical modeling. Right? For that, I think I should not take the chance of drawing. What I'll do, just a minute, I'll show you the example from my PDF itself. Because drawing will take a lot of time. I'll provide you with the PDF so that you can. Just a second, my computer is working in background. I don't know why. So have you understood this analogy, force, voltage, and torque current analogy? And depending upon your availability of source,
Yes.
current source and voltage source, you can choose either of the analogies. And this is not only applicable to mechanical system, any physical system having a second order differential equation with constant coefficients can be replaced by series RLC or parallel RLC circuit. It is not only restricted to second order system. Even if you have third, fourth, any higher order system, that can be equivalently represented in terms of this electrical network. It may not be a series RLC or series parallel or parallel RLC circuit. There may be other permutation combination, series parallel or other combinations, there may be. Let us now consider an example, after which I shall conclude today's class. Oh, I have not taken the example over here. Okay, I have to draw. Fine. Now, an example is nothing but a mechanical accelerometer. Sorry. That is, we will be measuring the acceleration of a moving vehicle using an accelerometer. It's a mechanical accelerometer. How it is the structure? Structurally, it is something like this. We have a frame like this. Within this frame, we have a spring. It's cited over here. Mass, damper arrangement. Okay, spring constant is K. The viscous friction coefficient F is a damper, is a mass M. And this is graduated on a scale over here. This is a 0 point of the scale. Okay. Now the concept is that this blue frame is actually the accelerometer, which is mounted on the surface of a moving vehicle. The surface of a moving vehicle, this is mounted. So it moves along with the moving vehicle, and the displacement of the moving vehicle is measured with respect to a static reference frame. So there's another scale. This is a 0 point. On this static reference frame, we are measuring the displacement of the moving vehicle with respect to this static reference frame, and this displacement is say x. Initially, say the entire moving vehicle along with this accelerometer are at standstill. Now, as soon as this mass, this entire thing starts moving in this direction, what will happen to this mass? Due to its inertia, it will get deflected in this direction, say by an amount y. Class teacher. এক সেকেন্ড হোল্ড করো। Okay, so this entire accelerometer, whenever it starts moving with the vehicle in this direction, this mass will be moving in this, start moving in this direction, and this will cause a contraction in the spring. Now this movement of y will continue until this spring produces, and this damper produces enough force such that the mass, the force that it experienced from this side is counterbalanced, so that the force produced by the spring and this damper in this direction will exactly counterbalance the force experienced by the mass due to this motion, the constant acceleration motion. What is acceleration? Say this motion with the acceleration a in this direction and is constant, suppose. So this will exert a force mass on mass m, and that will cause the mass to move in this direction. So this will be effectively the positive direction for y. For x, however, the positive direction is this, which refers to the static frame of reference, but the y is moving with respect to this frame of reference, and this frame is actually moving in this direction, x direction. Understood? So we have to find out the null position or the equilibrium position where the force produced by this spring. What is the force produced by the spring? K into y, right? What is the force produced by this damper? F y dot, right? These two forces will be, there will be another component of the force that is due to the motion of this mass. Since it is moving in this direction, there will be a inertial motion, inertial force. What will be that force? This force, that will be m what should be there in bracket in this direction?
Plus y minus x.
Y minus
Plus
x.
y minus x.
Right, exactly. So this is the force in this direction. I've written over here, right? So it will be very clumsy if I write over here. So these are the three forces acting on the mass. So at equilibrium, what will happen if the forces counteract the force experienced with the mass? So they will exactly will become at an equilibrium position. So the force equation, if you draw the force equation or from the free body diagram, the force equation will be m dt ct square plus fy dot plus ky. Okay, now the equilibrium position will be determined when this is equal to 0. Now if we just break down this y minus x component, what we'll have? We'll have m y double dot plus fy dot plus ky is equal to mx double dot. What is this mx double dot? Is nothing but m into a, acceleration, and which is equivalent to force applied on the mass. Right? Now if you consider that acceleration is constant, so an equilibrium point will be reached. And what is that equilibrium point? At that equilibrium point, the y will settle down to a value, say y0. Right? If y settles down to a deflection y0, then what about y dot? Sorry. Y dot will become 0 because y has now settled down to a particular deflection y0, and y double dot will again be equal to 0. So from this expression, what you will get? K y0 is equal to m into a. So the dynamic equation at steady state becomes an algebraic equation. From that, you can obtain this a as k by m y0. So it's a constant, obviously, spring stiffness is constant and mass is also constant. So it will be A is equal to k by m y0. So the acceleration will be given or can be read directly from the deflection y equal to y0. So see, there is a system. This system, it was when it was a steady state or standstill, deflection was y equal to 0. As soon as the vehicle upon which it is mounted starts moving, the mass will be deflected in this direction and it will continue to move in this direction until the opposing forces is equal. Forces are equal and opposite to the force forcing the mass to the left hand side. That will call the equilibrium point. And at equilibrium point, if deflection is y equal to y0, then that y0 will be direct indication of the acceleration. And this is based on the assumption that acceleration remains constant throughout the process. So in this way, a mechanical accelerometer can measure the acceleration as a function of this deflection, right? So what we have done here, we have obtained the dynamic model of the system. Not only that, we have find out how the system will respond at an equilibrium conditions, or when it reaches an equilibrium or a steady state. That will give you the desired result, that is the acceleration value. Okay, understood? বোঝা গেল?
Yes, sir.
ঠিক আছে, এটা একটা এক্সাম্পল আমি জাস্ট দিয়ে দিলাম। আচ্ছা, আজকে তো মোটামুটি 6টা বেজে গেল, আজকে আর আমি এগোচ্ছি না। নেক্সট ক্লাসে উই শ্যাল ডিসকাস অ্যাবাউট ল্যাপ্লাস ট্রান্সফর্মস। তুমি কি ল্যাপ্লাস ট্রান্সফর্ম পড়ে এসছো? জানো তো ল্যাপ্লাস ট্রান্সফর্ম? ওকে, তাহলে আমি ল্যাপ্লাস ট্রান্সফর্ম নিয়ে ডিটেইলসে বেশি আলোচনা করব না। What I'll do, I'll discuss about use of Laplace transform, application of Laplace transform, why this Laplace transform is necessary. Now let us have a preliminary discussion on that. তোমার Laplace transform কি রেসপেক্টে পড়েছো? On which respect have you learned the Laplace transform? কেন হঠাৎ Laplace transform ইউজ করবো কেন বা পড়বোই বা কেন?
স্যার সার্কিট সলিউশনে করেছি, মানে এর আগের সেমে আর কি।
কেন করেছো Laplace transform?
মানে স্যার ল্যাপ্লাস ট্রান্সফর্মে একই সাথে স্যার ইনিশিয়াল কন্ডিশন গুলোকে মানে একসাথে কনসিডার করা যায়, মানে অনেক ইজিলি সলভ করা যাচ্ছে,
ইজিলি সলভ করার জন্য।
রাইট,
মানে তার ট্রান্সিয়েন্ট রেসপন্স আর স্টেবল একসাথে আসে।
আর ডিফারেনশিয়াল ইকুয়েশন গুলোকে সলভ করার জন্য তোমরা ল্যাপ্লাস ট্রান্সফর্মটা ইউজ করেছো। Since we are studying dynamic system which are characterized by ordinary differential equation with constant coefficients, so we have to solve the differential equations to obtain the actual response of the system. But the response of the system will also be a function of the input to the system. Or if you change the parameter of the system, then for each of the situations you have to solve the differential equation repeatedly. Now solving a differential equation can be carried out by using simple method of integration, but in some situations that may be cumbersome to continue in repeated manner. So what you can do, you can use the help of a mathematical tool that is called Laplace transform, which transforms the integral differential equations in time domain to linear algebraic equation in frequency domain or complex X domain, right? So whenever an equation is converted into linear algebraic equation, then you can simply follow some algebraic manipulation to obtain the desired response. XS suppose in frequency domain. Then you apply inverse Laplace transform to obtain the desired response in time domain. So this operation, this converting the system from time domain to frequency domain via Laplace transform and then reverting back from Laplace domain to time domain, this operation will constitute the solution of differential equation. Now in the next class we shall discuss about different methods of solution of differential equations for different cases. Okay, different cases means I think you have the concept of poles and zeros. They have a concept of poles and zeros since you have learned that transfer function thing. Have you heard the term characteristic equation or roots of equation or roots of a differential equation? Anybody? In Laplace domain? Anyway, so whenever you are asked to solve a differential equation, you convert it to Laplace domain. Okay, in Laplace domain, what you will obtain is the algebraic equation and the roots of that particular algebraic equation of the denominator. If you get a polynomial function, ratio of two polynomials, that is a transfer function, then the roots of the denominator polynomial will be the poles of the system. Those situations may appear where the roots of the denominator polynomial are distinct. They may be repetitive. There will be poles of multiplicity more than 1, 2, 3, 4. In those situations, how to solve for the Laplace transform or inverse Laplace transform, we shall discuss about that. Okay, that's the partial fraction expansion. How to go for the partial fraction expansion. I'll discuss some typical cases. Okay, not in detail everything. I'll discuss some typical cases. And then we shall discuss the concept of transfer function. Now, I just give you a hint why this transfer function is necessary. Because you know, for a given system, the input, it may be subjected to different inputs. And for different inputs, to obtain different outputs, you have to solve the differential equation repeatedly. Even if you solve via that Laplace transform domain, it will not be very easy because the partial fraction may change due to the input function, a change in the input function. So to reduce that burden of repetitive calculation, what you can do, you can represent the system in terms of a transfer function, which relates the input of the system to the output of the system. So if you know the transfer function of the system, given any input, you can simply calculate the output in frequency domain at least. From that, later on, we'll see how this transfer function can be used in analyzing the system performance or synthesizing a system performance as per requirement. So to build up that concept of transfer function, we shall first study the method of Laplace transform and inverse Laplace transform to solve ordinary linear differential equations. Okay, so whatever Laplace transform theorems or method of solving differential equations that you have studied in previous semester, we just brush them up so that our discussion will be much faster. You can converge to a conclusion much quickly. And especially, you just revise back the different methods that we apply to solve the Laplace inverse Laplace or to obtain the inverse Laplace via partial fraction expansion. Okay, for different scenarios or different cases. Oh, so I shall discuss only a few typical cases where a simple intuition or a simple trick may help you a lot. For that, I shall not consider all the possible cases of inverse Laplace transform. Only some typical cases I shall discuss, and rest you should practice by yourself. Okay. So for today's class, I think I'll stop here. So any questions or doubt? Since you're all silent, I'll assume that there is no question or doubt. So I'll stop my class. Okay.